Okay, so we're going to look at some physics challenge questions based on electricity. So we've got a traffic light system, a cell connected to terminals X and Y. Explain how you connect the circuit to light a red lamp and how you connect it to light the green lamp. Okay, so what I'm going to need to use here is conventional current comes out the longer side of the battery, or the positive side, and for a diode to conduct we need its arrow to point in the same direction as conventional current. So to light the green, we'd go X to A, so the current goes along and goes through green. To get red, we'd go X to B, so the current goes along the bottom and then up. And that's how we'd get them to turn on. Okay, so you can switch to green by connecting a DPDT, never heard of one of those, but alright, a double pole double throw switch into the circuit, as you can see. Essentially when it's up, okay, so both of the switches are up, and when it's down, both of the switches are down. So first of all, show how you'd connect MN, P and Q to have that up lights the red light and down lights the green one. So to light the red with up and green with down, we'd connect M to B and A to P, and then to get the green with down, we would connect Q to B, and you do N to A. So that's the setting that we need there. So it says, what would you connect the traffic light circuit to operate both lamps at once? So we would need to change the supply. At the moment we've got a DC supply, so we're only ever going to have one or the other. If we want them both lit, we're going to need an AC supply, which doesn't actually light them both simultaneously, but if it runs at 50 Hertz, like it does in the UK, it will certainly look like they're both lit, because they're both lighting and dimming 50 times a second. Okay, so an electric locomotive is connected to 20 kilovolt supply. The return path of the current flows through two identical parallel rails. If an engine has a power of 5 megawatts, what is the current? So we're going to use P equals IV. So using that, the current is 250 amps. We've got two rails though, so it's going to have 125 in each because they're identical. So model rocket motors contain gunpowder, which is detonated electronically by a resistor. When the rocket is fired, a current of 5 amps is passed through for 0.5 seconds. Why does that make the propellant ignite? So propellants ignite if they get hot. So what's happening is the resistor is getting hot when the current flows through them, because it's converting electric potential energy to thermal energy. And when it reaches a certain temperature, it can ignite the gunpowder. Okay, so the battery pack is used to provide current, has a voltage of 4 volts. Calculate the energy transferred to the resistor before the propellant ignites. So I'm going to use these two equations here, E equals QV and Q equals IT. Put those together, we get E equals IVT, and then we can put the numbers in and we can see it comes out as 10 joules. So a similar technique is used in theatres to produce loud bangs, bright flashes or smoke. Here a 20 volt supply is used to detonate electronically specially constructed fireworks called pyrotechnics. For safety reasons, the explosive must detonate within 0.05 seconds of the current being switched on. Assume that the energy needed to detonate the pyrotechnic is the same as before. Calculate the current needed to detonate within 0.05 seconds. Okay, so we're going to use the same equation, but we want to find current. We know energy from before, we've got the voltage, we've got the time, so you can see we now need 8.3 amps. Calculate the resistance of the pyrotechnic. So we can use this equation here, R equals V over I, plug in the voltage, plug in the current, and we can see we get the resistance. So the resistor functions as a detonator in the pyrotechnic. It is a piece of thin metal wire. Will its resistance change as current is passed? If so, will it go up or down, and why? So as the current passes through the conductor, its temperature will rise, and if temperature rises, resistance rises. And the way I think about that is each charge passing the resistor is going to collide with more particles every second, because all of the particles have much more energy at higher temperature. So this question estimates the voltage of a thundercloud. We start with a simpler situation. Two parallel plates of metal are held 5 millimeters apart, and a voltage of 5,000 volts is maintained. Okay, so we've got a 5 millimeter separation, 5,000 volts. Okay, state how much energy would be required to move a unit coulomb charge from one plate to another. So we can use E equals QV. Our charge is 1. We're trying to move it through a potential difference of 5,000. So we're going to need 5,000 joules of energy. If a coulomb of charge is transferred from one plate to another, state the relationship between the energy transferred and the force on the charge, assuming force is constant. Well, we know how much work we've had to do to transfer the charge, and we know the distance that we transferred it. So doing work done over distance gives us the force required. Your answer to B is equal in magnitude to electric field strength, which has the unit of volts per meter. This is equal to the force per coulomb of charge placed between the plates. So what that really means is the electric field is a constant, but if you double the charge, that's going to double the force on that charge, essentially. So when the voltage is raised to 15 kilovolts, a spark forms. What is the electric field strength between the plates now? So we saw that the work done was directly proportional to the voltage. And so if we've got 3 times the voltage, we're going to have to do 3 times as much work to move the charge across. We also saw that the force per charge, or the field strength, is proportional to the work done, because we haven't changed the distance. So therefore we're going to get 3 times the field strength, so 3 times 10 to the 6 newtons per coulomb, or we could have it in volts per meter. It's the same thing. What voltage would be needed to produce the same electric field strength between the ground and the base of a thundercloud at an altitude of 1,500 meters? Okay, so all we've got here is this expression, and this essentially comes from what we had before. So field strength is force per charge, so I'm going to divide the work done by charge, we get the VOD. So that's where that's come from. And then what we do is we can plug the numbers in, and we can see we need a potential difference of 4.5 gigavolts, or 10 to the 9 volts. So this is a kind of a ballpark answer, but you can see kind of the how big it has to be. So a child who climbs up on a pylon and touches a high voltage power cable is almost certain to be killed. Why can a bird perch safely on the same cable? Well, the bird doesn't touch the pylon. The bird just stands on the cable and is insulated from the ground, whereas if you climb the pylon, you're connected via the pylon to the ground, and when you touch the cable, you're going to have a massive current that goes through you, which is likely to send you into fibrillation or have a heart attack, essentially. So any object that is isolated electrically from Earth can store electric charge. For example, you've probably experienced a buildup of static charge on your clothes on a cold, dry day. The diagram shows a plate X electronically isolated from another plate Y. The lower plate is earthed, and the cell is used to charge up the top plate. Okay, so we're going to build up positive charge on plate X because it's connected to the positive terminal of the battery. And these two plates form something called a capacitor, which you will probably never come across before unless you've done some extra reading. Indicate by arrows on the diagram the direction in which electrons move. So conventional current, remember, the flow of positive charge comes out of the big side, so electrons therefore come out of the small side. So Y will end up with a negative charge, X ends up with a positive charge overall anyway. Okay, so the amount of charge capable of being stored on X plate gets larger as you increase the voltage. So the bigger the voltage, the more charges you can store on plate. It's what that's saying. The ability of the X plate to store charge is called capacitance. The quality measures the extra charge stored each time the voltage is increased by 1 volt. So essentially what we can do is we say capacitance is the charge you stored per volt. And that means it's going to have the unit of coulombs per volt. But incidentally, for those of you interested, it is actually given a name and it's called a farad after Michael Faraday. Okay, so a small memory card takes a 20 milliamp current from a 12 volt supply. Its battery is connected in parallel with a capacitor, which charges up to 12 volts. The X plate has 0.07 units of capacitance. Okay, calculate the resistance of the memory card. So we can use V equals IR or R equals V over I, whichever way you try to start with. We've got the potential difference, we've got the current, so we can see the resistance is going to be 600 ohms. Calculate the charge stored on the plate. Well, we had the equation C equals Q over V, so we can rearrange that to Q equals CV. So you can see it's 0.84 coulombs of charge, or an absolute boatload of electrons if you want to think about it that way. A battery is removed for replacement. It must be changed before the capacitor runs out or the data is lost. Estimate the time required to change the battery before the data is lost. So I'm going to assume the current is the same as the one we had before, and we do Q divided by I gives us 42 seconds to do a turnover. So we're going to have to, it's not massively quick, but that's a pretty quick turnover. Give two reasons why the time you've calculated is only an estimate. Indicate whether that would mean it's too long or too short. So the first thing I thought of is, as the amount of charge on the capacitor decreases, the force repelling electrons off the capacitor is going to decrease. So we're going to get a smaller current as time goes on, and that's going to mean it discharges slower and slower, and so essentially that time is actually too short, it's going to be bigger. And actually for a capacitor, current follows an exponential decay. But the other thing to think is the memory card might fail before the voltage drops to 0. So actually maybe that time is too long, or maybe these two effects kind of cancel each other out, and that ends up being a reasonable estimate.